Pre-cal.
Hey there. Today we're going to talk about domains and ranges and make it a little bit more difficult by also using them within operations of functions, meaning we can put a function and add it to another function, we can subtract them, multiply and divide them, and we'll get to that. So first let's talk about adding two functions together. So over here we have f plus g of x, and that notation, what that means, which can be sometimes confusing, simply add f of g plus g of x. It just says that when you're adding two functions and each of those functions are to respect of x. So over here, let's say we have f of x equals 2x squared plus 3, g of x is 4x cubed plus 1, and then you add the two together. F plus g is just simply adding this and this, and then when you add like terms, you get this right here. So it's not too bad so far. When you subtract the two, it's the same thing. The only thing you have to watch out for is when you have f minus g, you have to make sure that the entire g is being subtracted. What I mean by that is when you have this function minus that function, make sure you distribute the negative into this function. A lot of people might accidentally just put negative 4x cubed. And then again you add like terms and you will end up with the final answer. The product of f of g. So let's say we have f times g and then in parentheses and then we have x right there. That should equal f of x times g of x. We're just trying to talk about the human convention, how we write operations of functions. So instead of writing f of x times g of x, we may just write f times g, and that's that both functions are to respect of x. So our resulting function should also be with respect of x. So when you look at this, f of x looks like that, g of x is this. This is just an example. By no means does this have to be it. When you do f times g, you have this guy, which is the f function, times the g function, and then you multiply it out, you FOIL out. So you FOIL the first term with the last term, the last term with the other last term. So it's like firsts, lasts, outer, inner, lasts. I think that's what FOIL stands for. And then we add like terms. There we go. Let's continue. The quotient of f over g, what that pretty much is when we write down f over g to respect of x, we just want to divide the f of x function by the g of x function. So if this is the f of x function and that's the g of x function, it will simply be the f of x divided by the g of x. And make sure that if you have a denominator, it has a radical to get rid of the radical appropriately. So pretty much this was a square root of 4x cubed plus 1. You multiply by square root of 4x cubed plus 1, top and bottom. Now this is the difficult part. Finding the domain of a function can be hard enough, but when we have composite functions, it can be a lot more difficult. And this is pretty much what the video is going to be focusing about the most from this point onwards. Let's talk about composite functions. So let's say we have f of g of x. So they're both functions are to the x to respect to the x variable. So what happens here is we take when we rewrite it into something that we're more familiar with, we write it as f with inside of f we put g of x. So here's how it looks like. Let's say we have f of x being this and g of x being that. Since I'm saying g of x will go into f, we'll take whatever g of x is and then we lead back to the x that is in the f function. So 2x squared plus 3, where there is an x, we'll put this stuff in there. So we have, instead of having x, we have 4x cubed plus 1. We square that because it was x squared, and then we multiply by 2, and then plus 3. So when you FOIL this out, you should, and multiply by 2, you should end up with this, and then plus 3 leaves you to just add like terms. So 2 plus 3 is 5, which is how they got that. When you have the other way around, meaning you have g of f of x equals g of f of x, we take the f function this time and put it into the x of the g function. So what used to be squared in the previous one now is being cubed. So you can see that the answer would definitely be different. So let's see that. Let's see what happens. We take the f of x, so 2x squared plus 3, and put it where it says x. And then that's being cubed. Now the reason why whoever made this PowerPoint stopped is because when you cube a binomial, it can be a little bit time consuming and the screen would be filled. So they just pretty much stopped right there. So for my class, I will probably do the same thing. I say if you get to this point, I am totally satisfied. You don't have to go any further. When you write f of g, you're pretty much taking a function and putting it into itself. So sometimes we try to confuse you by having an f of x and a g of x. This is completely useless in this case, because all we're doing is we're taking the f of x function and then putting it into itself. Where there used to be an x will now be a 2x squared plus 3 squared, and then multiply by 2 and then plus 3. And you pretty much solve that out and get, what would that be? That'd be 4x to the 4th plus 12x squared plus 9, and that's being multiplied by 2, and then you pretty much add 3. The domain of composite functions. Now this is where it can get really tricky. We're trying to figure out what the domain is of a function, and it can be kind of difficult because one function's range, which is pretty much what the output is, the y, can be another function's domain. So we'll do an example right now. So if you have f of g, and what that means is we're putting the g function into f, and you're trying to figure out what the domain is of this function, then you kind of have to think about it. The domain starts off with whatever we put into g, right? So what can we put into x right here? We can put any number that is equal to or larger than 1, right? So that's what goes in here. This function, this domain, allows you to have 1 and bigger numbers. However, it goes into the denominator of a different function. So what happens now is this function is not allowed to be 0. So what used to be 1, you are allowed to have a 1. Because you're allowed to have a 0 inside the square root, because it ends up being in the denominator, the domain of the function now should say x can be bigger than 1, but can no longer be equal to 1. Because if x is 1, that's a 0, which would make it a 0 down here, so 1 over 0 is just unacceptable. And then finding the range is another story as well. The only thing I would like to say to my students is when you do write this down, make sure to write it in interval notation. The interval notation would go like this. We need a number bigger than 1. So to emphasize bigger, right, but not including 1, we use a parenthesis. That means not including 1. And since we're saying bigger, it's 1 towards infinity. And since infinity is a theoretical number that can never be reached, we would also use a parenthesis here. What this would mean, if I had written it like this, if I would have used brackets, what this means is the domain is 1 all the way to infinity, including infinity. So that's kind of bogus. Well, for one, we cannot have 1 because it would make the denominator 0. Also, you cannot have infinity because infinity is like this fruit that you want to eat. However, that fruit is forbidden. Well, that's a really bad example, but it's just too big. You can never reach it. All right, let's move on. So let's do this example right here. So you can see that we're trying to get g of f of x. So what that means is we take the f of x function and put it into the g of x function, and we kind of figure out what the range and domain is. Well, to me it looks like x can be anything when you look at this. However, its range, although it could be anything, is essentially the domain for this guy. So we kind of look at this guy and we look at ourselves. This cannot have x equaling 1, because when x equals 1, right, we have 1 over 0, because 1 minus 1 is 0. So let's look at this. Let's go backwards again. So essentially this cannot be 1. What x would make this function 1? Well, if x was 6, then we would have a 1 here, right? Because 6 minus 5 is 1. So x can essentially not equal 6. So our domain would look like this. Aren't you happy that you're sitting at home watching me do math? Yeah, of course you are. So x cannot be 6. However, I can have numbers below 6 and above 6. So we can have a domain that starts at negative infinity, but we are not including infinity, and goes all the way up to 6. However, we can have numbers above 6, so we create a union. This is called a union. And we're going to union an interval that starts at 6, not including 6, and that goes all the way to infinity. So saying a number x cannot equal 6, what that in interval notation is alrighty, all numbers below 6 and all numbers above 6. But in neither case did I include 6. Alright, that's our domain. Now when we talk about the range pretty much you look at the end result when you do plug everything in. X cannot be 1, right? But what this function essentially looks like, if you were to draw it, would look like this. You kind of have to understand how a function looks like. That function, I try my best. I will definitely try my best. Should look something like this. That looks terrible. That looks so bad. But you can see how y, which is the range, cannot equal 0. Because as we're going down, I'll try this one more time. We're getting close to 0, but we're not quite getting to 0. And this way as well. We're starting at negative infinity, we're close to 0, and then we're going downwards. But we never touch 0. So the range would look like this. The range would be negative infinity to 0, and we're going to union 0 to infinity. There we go. That's our range. And you may want to write down D and R. D and then R. Alrighty, let's move on. So let's talk about f of g, meaning we're putting the g function to the f function. So you're taking this guy, which is g of x equals 1 over x minus 1, into x. So that's x minus 5. So essentially we're pretty much starting off here. And we know that our domain right off the bat cannot be 1, right? And over here we wouldn't have a problem. So that won't affect it at all. So our domain is just simply, we pretty much start with what we begin with and then what we put into. X cannot equal 1. So you would write the domain in a way where you display x cannot be 1. So the way that would look like is, where's my pen? Oh, there it is. You would write down domain because you want to make sure Mr. S is happy with you. You would have to write down D. Domain is negative infinity. I'll do this so many times. I know it seems silly, but if I do it a million times, you will be so comfortable with it. Union, and then 1 to infinity. That means numbers below 1 and numbers above 1 put together. One big happy family. And then we have a range that we're going to calculate. And let's see what happens here. When you put this guy into here, we know that this thing will never equal to 0. Because there's nothing I can put into x that would give me something that would cause this to go 0. So essentially, since this can never be 0, the function can never be negative 5. Because when I plug in 0 here, I would get negative 5. And this can never be 0. So the range cannot be negative 5. Does that make sense? We start with the beginning. This is the beginning. We put that into here, right? We know that this whole thing cannot be, with the beginning cannot be 0, and when we put the beginning into the final place, right? That's the beginning and that's the final. Then we know that this can never be negative 5 because this can never be 0. So therefore our y, our range, cannot be negative 5. So you would, let's see if I can do it with the mouse. Range. Oh, that looks a little unprofessional. Let's go ahead and stick with that. Whoa, I changed colors. So negative infinity all the way up to, at this point you can actually say it with me, and then negative 5 all the way up to infinity. There we go. That's our range and domain. You are so good at this. This is just pretty much saying the answer. Let's say we have a problem like this. So in this case we're saying g of f, meaning we're putting the f function into the g function. So here's our f function, we're putting that into here. We're starting with this guy. I don't have a problem except if this is negative, so it can be anything 0 or above. When I put it into this guy, this doesn't have a problem with anything. That's just a polynomial. And when I say problem, I'm saying, is there an x value that would make this go bad? And no, there isn't. So over here, this one can never be negative. So our domain right off the bat is going to be x has to be equal to or greater than 0. The way that would look like is in interval notation. We can include 0, but we cannot include infinity because we cannot reach infinity. So that's our domain. Isn't this fun? Yes, it is so much fun. And then we talk about the range. Our range looks like this. This can never be negative. The f can never be negative. So since that can never be negative, over here, the inside of an x can never be negative, right? It's always positive, but it does grow. So we do start off with, this will never go below 0. So we will never have anything below 0 in here. So we square that, which means that we pretty much start at 0 and go upwards. So our range is pretty much the same thing. 0 all the way up to infinity. Now, one difference is though, if you were to calculate this guy out, if you were to put this function into here, essentially you would get a square root of x and then you would square it, which essentially gives you x. So I know what you're thinking. Hey, Mr. S, that's a line. So what I can simply do, I can just go ahead and do this. This function, because I'm so cool, I'm going to go ahead and draw it, will look like this. And I will say no. Okay, stop right there. You know that the domain is 0 to infinity. What are you doing using all these values that are x being negative? The function is supposed to look like this. Bam. It's supposed to look like a line, actually. Let's move it a little bit right there. Bam. I wish I could make it straight, but that's okay. So that's how it looks like. So although the function solves out to be f equaling x, it doesn't follow the same function because the domain is different. The domain was altered because we used two separate functions to get there. Alrighty, next. Let's say we have a situation like this, and over here we taking this guy and putting it into the f function. Over here, x has to be 2 or bigger than 2. I don't have a problem here, so domain is just pretty much 2 or bigger than 2. So what that would look like is bracket notation. Mr. S, you're using way too many examples. I have things to do. Well, you know what? Chill out for a little bit, okay? Just do this for me. That's your domain right here. And that's a really weird D. That's your domain. So when we talk about the range, we're taking the g function, putting it into here. We know that this is a growing function. It starts at 0 and goes upwards. So over here, it starts at 0, and we're multiplying 0 by 2, and then we go upwards again. So it starts at 0 and goes up to infinity. That's how we kind of figure that out. So the way that would look like is we start at 0, but we go all the way up to infinity. Oh, whoa. There we go. Very good. That's our domain and range. I'm feeling pretty confident right now. And that is it. Have a good day.